Hello everybody, welcome to our pressure and gas laws video. So let's begin by talking about what's sometimes referred to as the kinetic theory of gases. And so this theory states that gases are made of small particles, and by small particles we mean atoms and molecules, and these travel at very high velocities. So compared to a solid or a liquid where the particles are kind of stuck together, gases, the particles are just kind of zooming around freely. And they have essentially no interaction with each other. So what that means is because our gas is mostly empty space and our particles are moving around really fast, they don't really attract or repel each other very much. They do bounce off each other, but they don't stick together the same way a liquid or solid does. And they have kinetic energies that increase as temperature increases. And this probably sounds a little familiar from our unit about rate of reaction. The higher the temperature, the faster these particles are going to be zooming around. So keep these ideas in mind. Our particles are zooming around, and the higher the temperature, the more they zoom. So gas pressure is measured in a bunch of different units. In this class, we're going to be focusing on atmospheres, millimeters of mercury, and millimeters of mercury are also sometimes called torr. So torr and millimeters of mercury are the same thing. And additionally, we have some units that we see sometimes. This one pops up in physics. We won't be dealing with pascals very often. But pounds per square inch is something that you may be familiar with. People also abbreviate this as PSI, which again stands for pounds per square inch. And so what this refers to is that actually how many pounds of force are applied to each square inch of surface due to the gas particles. And so how does pressure come from the motion of the gases? Well, if we think about these particles zooming around, you'll notice that they actually bounce off the walls of the container. And as they bounce off the walls of the container, they're going to exert a force. And so these particles zooming around really fast as they hit that container, that's what creates our pressure. And so the more particles we have, the higher the pressure, or the faster our particles are going, the higher the pressure. Alright, so I'd like you to now pause the video and please complete questions 1 and 2. Welcome back. So we are now going to talk about 3 different gas laws. So the first one is what's known as the combined gas law. So as the name implies, this takes a bunch of smaller laws and combines them into one bigger gas law. And it states that our starting pressure times our starting volume divided by our starting temperature equals our final pressure times our final volume divided by our final temperature. And so some things to note here are that pressure and volume can be in any units we wish. So we could use whatever units of pressure, whatever units of volume we want, as long as they're in the same units. In other words, P1 and P2 must have the same units, V1 and V2 must have the same units, but other than that we can use whatever units for volume we'd want. Like for instance, we could use tablespoons or something. And from there we have also temperature. And our temperature is restricted. Our temperature must be in kelvins. So we can't use Fahrenheit, we can't use Celsius, we must use kelvins here for our temperature. And the reason for that is there's a couple things. 0 Kelvin means 0 motion for our gas particles, and so the higher that temperature, the more motion we have. So it works really well for sort of measuring how much particle motion we have. But additionally, the Kelvin scale never goes negative, and we can't have things like negative volumes and negative pressures, so we must use kelvins here rather than Celsius or Fahrenheit. So here we have an example problem. A 0.18 liter sample of gas with pressure of 0.8 atmospheres, 0.800 atmospheres at 29 degrees. At what temperature degrees C will this gas have volume of 90 milliliters and a pressure of 3.20 atmospheres? So when faced with a problem like this, I really like to make a table of data. So we're going to make a table showing us P1, V1, and T1, as well as P2, V2, and T2. So pressure 1 is given right here. So there's our P1. So we insert that in our data table. And then our volume 1 is given here, 0.180 liters. And then we're told we're at 29 degrees C. And so we have to convert that to kelvins. And thankfully, it's a very simple conversion. We take 29 and we add 273 to it. So that gives us a value of 302 Kelvin. Alright, so from there the problem specifies that our new volume is 90 milliliters. We're going to have to convert that into liters so our units are consistent, because we have to have the same units here. And our new pressure is 3.20 atmospheres. That's given right here. And then our temperature 2, our new temperature, that's what we're trying to solve for right here. So we're going to have to take our combined gas law and do some rearrangement of it. So we're going to have to take our equation, we're going to have to solve for T2. So in order to do that, we're going to have to do an algebraic rearrangement. We're going to have to shuffle stuff around. If you don't know how to do this type of algebraic rearrangement, if you can't arrive at this right here, I suggest you visit the math tutors at the LSC. They should be able to help you with this type of rearrangement. And I realize some folks might have forgotten. It's not the kind of thing you use day to day, so don't feel bad if you don't remember how to use it or how to do this. Just get help as soon as possible for how to rearrange these equations. So once we've finished our rearrangement, we can plug in our data. So we plug in our values from the table that we made previously. So P2, V2, T1. We get those from the table here. So here's our P2, V2, and T1. And then we plug in our P1 and our V1. And notice our unit cancellation here. Atmospheres cancel, liters cancel. We're left with kelvins, which is good because we're looking for a temperature measure. And so if we do all our number crunching, we end up with 604 Kelvin. So that's good, we're close, but the problem is we're asked for what temperature in degrees C. So we have to convert from kelvins back to degrees C. To do that, we simply subtract 273, or if you want more sig figs, it's actually 273.15, and we end up with 331 Celsius. So that is the combined gas law. I'd like you to now pause the video and please complete questions 3 and 4. Alright, welcome back everyone. Let's now talk about our next gas law. Let's talk about the ideal gas law. So the ideal gas law, we're going to be looking at pressure, volume, and temperature, and we're also going to take into account our number of moles. So our equation that we usually use is PV equals nRT. So a common question that comes up is how do we know when to use ideal gas law and how do we know when to use combined gas law? So I can give you a couple important tips here. The first tip is notice that this equation has only one pressure, one volume, and one temperature specified. So that's a clue. If you see a question that mentions two different pressures and two different temperatures and two different volumes, it's probably a combined gas law problem. Another thing to note here is if we see moles mentioned here, if we're dealing with moles and N, that's a good clue this might be an ideal gas law problem, because if we go back to our trusty combined gas law here, N or moles aren't measured. So here's our ideal gas law, and so units are important here. Pressure is going to be in either atmospheres, torr, or millimeters of mercury. Volume must be in liters. N is going to be in moles. Temperature must be in kelvins as specified here. Don't forget to use kelvins for the gas laws. And then R is a constant. So where do we get R? Well, if we plug in some values right here, we can solve for R. And so we have R both in atmospheres. So this is the value of R you're going to be using if your pressure is in atmospheres. And this is the value of R that you'll be using if we have millimeters of mercury or torr. And so I want to point out here, notice we have some kind of crazy units going on. These are just here so all our units cancel out properly. So pay attention to the units. They're a bit complicated for these values of R, but I do provide these for you on quizzes and exams. Alright, so let's look at an example problem. Dinitrogen oxide, also known as nitrous oxide, is laughing gas, and it's used by dentists. So if we have a 20-liter tank, 20.0 liter tank of laughing gas that contains 2.86 moles of N2O at 23 degrees C, what is the pressure in milliliters of mercury in this tank? So I like to make a data table just like we did before. Pressure, volume, moles, and then temperature. And so our pressure here is going to be unknown. That's what we're trying to solve for. So we're trying to solve for that pressure. And then our volume is going to be our 20.0 liters. N is given in the problem here is 2.8 2.6 moles. So, and then finally our temperature is 23 degrees Celsius. And so we're going to have to convert that to Kelvin. So there's our little table of data that we've extracted from our word problem. And now we're going to plug in some values here. So here's our table. So here we have an ideal gas law problem. We're going to be looking at nitrous oxide, also known as dinitrogen oxide or laughing gas, and this is used by dentists as an anesthetic. And so we're told in our problem we have a 20.0 liter tank of gas that contains 2.86 moles, and our temperature is 23 degrees C. What is the pressure in millimeters of mercury for the tank? All right, so here we have a data table we're going to create. So we don't know our pressure because it asks us what is the pressure. So you see things like what or how much, that's probably going to tell you what the question's looking for. So here's what we're trying to find. But the rest of these are given in the problem. And do note that we always need to use kelvins for our gas laws, and so we have to convert our temperature in degrees C into 296 Kelvin. And how do we know which value of R to use? Well, that's simple. The question specifies that we're looking for millimeters of mercury, so we're going to want to use R in millimeters of mercury. So now we're going to take our ideal gas law, and we have to rearrange it. So PV equals nRT, but rearranging that becomes P equals nRT divided by V. And from there, finally, we're going to sub in values. So here's our N, R, and T. So we plug those in from our data table. Here is our volume in liters. I want to point out, just so there's no confusion here, here is our gas constant. So notice that some of our gas constant ends up sort of down below in the denominator section. So there's our gas constant. And if we crunch all our numbers, we end up with a pressure of 2.64 times 10 to the third millimeters of mercury, or 2,640 millimeters of mercury. All right, so I'd like you to now end this video, and we'll be continuing in part number 2. And please complete questions 5 and 6. Thank you.